let's begin. So for chapter 30, we'll talk about all this stuff, from Faraday's law, Lenz law, induction of energy transfer, induce electric field, blah blah blah, and we'll talk about the inductance, self-induction, mutual inductance, energy stored in the magnetic field, energy density. So first, we'll talk about the Faraday's law, which is actually the last law in the Maxwell equations. So let's consider the first experiment. A conducting loop is connected to a sensitive ammeter, which means a meter to measure the current, and sensitive means it can measure a small current, very very small current, which is what this sensitive means. And because there are no battery or no other source of EM induced, there is no current in the circuit. Yeah, no current. There's no battery. Should have no potential difference between any 2 points of the loop, and there shouldn't be any current. However, if we move a bar magnet toward the loop, the current suddenly appears in the circuit. The circuit disappears when the magnet stops moving. So this is due to the movement of the magnet bar, not actually the existence of the magnet bar. Do you get this point? 就是说，它跟那个磁棒的移动有关，它不是说你放在那边它就会有电流，就是说你把那个磁棒移进去这个 loop 里面的时候，它会出现一下子，然后那个磁棒在里面停下来的时候就没有电流。So if we then move the magnet away, a current again suddenly appears, but now in the opposite direction. So if we experiment for a while, we would discover the following rules. So a current appears only if there is relative motion. Relative motion is very important here. So between the loop and the magnet, one must move relative to each other. You can move the magnet into the loop, or you can just move this loop towards the magnet. The current disappears when the relative motion between them ceases. When they don't have relative motion, then there will be no current. So faster motion of the magnet produces a greater current. If moving the magnet's north pole towards the loop causes, say, clockwise current, then moving north pole away causes the counterclockwise current. So the pole of the magnet really influence the direction of the current, or the direction of the electromotive force. So moving the south pole toward or away from the loop also causes current, but in the reverse direction from the north pole effects. So here we have the second experiment. For this experiment, we use the apparatus with 2 conducting loops close to each other, but not touching. So it seems like it looks like the setting for the experiment 2, the magnetic induction, but actually it is a much larger apparatus than this schematic. Okay, if we close switch S to turn on the current in the right hand loop, the meter suddenly and briefly register current and induce current and induced current in the left-hand loop, which means if this switch is open, there will be no current. So there will be no magnetic field generated by this loop, and this one don't have current. If you turn this on, which means you short this switch, then there will be a sudden and brief registered current. So this current only appears for a short moment. If the switch remains closed, no further current is observed. If we then open the switch, another sudden and brief induced current appears in the left-hand loop, but in the opposite direction. In the opposite direction. So you feel like this case. Feel like this. So if this is the time, and this is the current. Maybe you consider clockwise. Maybe I'm not sure. So if you originally there are no current, it should be 0, and you suddenly turn on the switch, it will go up and down. Just appear for a short moment. In signal and system, you know this is called the delta function. The delta function. So you turn on the switch, then there will be some current. And as the switch is closed, which means there are current, but there will be no current here. No current for this one. No current for this one. And you turn this off, then you have another one. So it will be I0, I minus I0 delta T minus T1, somehow like this. And then you will have no current again. Okay, so when the current in the right-hand loop is charging, either turning on or turning off, and not while it is constant, even if it's large, the induced EMF, induced current in this experiment apparently caused when something changed. But what is that something? Faraday knew. So actually, it's due to something is changing, then there will be current in this loop, rather than I make this current very large. I make this battery to be double or triple. It doesn't really influence that stuff. As long as this loop has a constant current, then there will be no current for the other loop. So actually, in the experiment, you make it a AC source, so there will be constantly, which means the current in this loop are currently changing. So the current in this loop will not be 0 at any almost any moment. But yeah, you know the sine wave, there will be some 0 point. But so actually, this is the Faraday's law of induction. Faraday realized that an EMF, electromotive force, and a current can be induced in a loop in our two experiments by changing the amount of magnetic field passing through the loop. He further realized that the amount of magnetic field can be visualized in terms of magnetic field lines passing through the loop. So similar to what we have defined in chapter 23 for the electric field, we also define the magnetic flux phi b through an area A in the magnetic field. B is defined as this one. Actually, we don't have a circle here. It doesn't mean a closed surface. It only means this surface. So which this is actually not closed. So we only have a simple integral sign here, or you can draw a double integral sign. Doesn't really matter, but the notation for the physics textbooks and the calculus textbook are somehow different, you know. But actually, we define the magnetic flux as the B field dot the dA, the area vector, and then do the surface integration, So while the integral is taken over the area, the SI unit of the magnetic flux is the Weber. So for the magnetic field, we use the Tesla. So actually, the SI unit for this one is Tesla times area, which is meter square. So 1 Tesla meter square. And actually, we use Weber for the magnetic flux. So if B is perpendicular to the area and uniform over it, the flux is phi B equals BA. So maybe you have learned it in high school. So Faraday's law of induction, the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux phi B through the loop changes with time. So actually, the simple form can be written like this. So E is the EMF, electromotive force, and phi B is the magnetic flux, and then we take the derivative with respect to the time, and take the minus sign, This minus sign is important. Yeah. So for coil of n turns, we just have another n factor. Because you can add all the magnetic flux to the same loop. So the induced EMF tends to oppose the flux change, and the minus sign indicate the opposition. This minus sign is referred to as Lenz law. So only the minus sign in the Faraday's law is called the Lenz law. So it is so just like in 200 years ago, if you can find a minus sign, then the law will be named after you. So it's quite different from now. Well, Lenz law. I'm not sure where. Yeah, maybe we have you can have a sample problem here. So actually, we have a long solenoid S, which is the blue one, has 220 turns per centimeter. Carries a current I equals 1.5 A. So its diameter D is 3.2 centimeter. At its center, we replace 130 turn, which is the orange one, closely packed coil. C of diameter D, which is slightly smaller, the current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. 25 milliseconds. So at the beginning, it is I equals 1.5A, and it reduced to 0 in 25 milliseconds with a constant rate, which means linearly. What is the magnitude of the EMF that is induced in the core C while the current in the solenoid is changing? So first, we calculate the magnetic flux. The magnetic flux. Phi B, which is actually B times A So in the previous chapter, we know that the magnetic field generated by a solenoid is N mu 0 I N mu 0 I N and times the area times the cross-section area. So mu 0 is nothing but 4 pi times 10 to minus 7. I is 1.5. And then N is 220 turns per centimeter. So per meter, it should be multiplied by 100. So it is 22000. And the cross-section area should be pi for the large one, which is not the large one, should be the smaller one, 0.021 square. Diameter should be divided by 2. So the radius will be 0.021 over 2 square. Yeah, because it's consider the magnetic field generated by the solenoid, and actually we only consider the magnetic flux for the small coil C. So we only consider this radius here. So the radius should be 2.1 centimeter over 2 over 100. This is for the meter. So because of diameter. So we need to divide by 2 to be the radius. So actually this one should be 1.44 times 10 to minus 5 Weber. So this is the magnetic flux at the very beginning. So because it is the current is changing is reducing in a constant speed. So d phi b dt should be minus 1.44 times 10 to minus 5 over 25 milliseconds. So 0.025, which is minus 5.76 times 10 to minus 4 Weber per second. Actually, this one is actually the same as volt. So according to the Faraday's law, we know the electromotive force should be negative n d phi b dt. d phi b dt. So so that one is 130 turn. So we have minus 130 times this minus 5.76 times 10 to minus 4. And the answer would be 75 millivolt. Any questions? Any question regarding to this one? Okay, let's talk about more about the Lenz law, because to really know the direction of the electromotive force is not straightforward. So let's talk about it more. So an induced current has a direction such that the magnetic field due to this induced current opposite to the change in the magnetic flux that induced the current. The induced EMF has the same direction as the induced current. So Lenz's law at work as the magnetic field is moved toward the loop. The current is induced in the loop. The current produces its own magnetic field with the magnetic dipole moment oriented so as to opposite the motion of the magnet. Thus, the induced current must be counterclockwise as shown. So you can see that for this one, this magnet bar should have a should have the direction like this, which means that it should be like this. And if it moves closer to this loop, it will become stronger. So this loop will try to induce an electromotive force that will generate another magnetic field, which will counteract to this change, which looks a little bit complicated. Yeah. So it turns out that the rate of change of the magnetic field will or the magnetic flux according to this loop is smaller than what you really want. 我用中文重复一次，就是说，这个磁棒啊，就是它有一个磁力线往这个方向，大概往下面的，就对于这个圈来说，那它往下的时候，那个磁力会更强，所以等于说这个这个圈的那个 magnetic flux 就会变大，而且是往下放的。 那这个圈呢、就会尝试去产生一个 electromotive force，这个 electromotive force 会产生也会产生一个 magnetic dipole，跟这个改变的方向相反，就是会抵消掉一部分的改变，因为它改变是往下增强的，所以它就会产生一个往上的magnetic dipole。那往上的 magnetic dipole 按照右手定着的话，它就是逆时钟的，逆时钟。所以那个 electromotive force 就是逆时钟的。So here we have some more small figures to demonstrate this idea. So at the beginning, there. So we have a loop here, and there is an increase the external. There is an external field induced current with the field that opposite the change. The induced current create the field trying to offset the change. Let me see. So at the very beginning, the B field, the external B field, increase the so the B field points to downward. And then if you increase it, then the magnetic flux with respect to the area will also increase and point to the downward. So for this loop, it will generate an induced B field which point to the opposite side, which is upward. So we have this one. This one is generated by this loop itself. This loop doesn't have any battery. We only change the external B field to the cross section of this loop. Then you will generate a B field and generate the B field by having a current, counterclockwise. So we demonstrate the I and also the EMF is also with the same direction. So it will point to this side, and if we start to decrease the external B field, if we start to decrease the B field, then which means that the magnetic flux to this loop is decreasing, which means that it should generate a B field point to downward to counteract these changes. So you can see that this one is smaller and become bigger. So in the left hand side, it should generate a B field point to the upward. So from this one to the next stage, the external B field decreases, which means that the change of this loop of the magnetic flux is point to this side. So it should generate an induced B field point to downward to counteract these changes. So as long as this one is decreasing, the induced B field point to the downward. And as long as the induced B field point to the downward, and using the right hand rule, the electromotive force is clockwise, and so as the the current direction. And next, if the external B field further decrease until it point to upward, the induced B field will still point to downward because it decrease and then point to upward and then further increase. So the induced B field will still point to downward. And as long as it has changed to the maximum value and start to decrease, largest one, middle, and the smallest one, and then the induced B field will point to upward. So the induced B field is not related to the direction of the external B field. It only relates to the changes. So you cannot just see the B field and then to determine the induced B field. You need to take the derivative with respect to the time, which means the rate of change is related to the direction of the induced B field. So this is what the Lenz law mentioned. Okay, so next, a conducting loop. So a conducting loop consisting a half circle. So we have a battery here. So we should have some current going counterclockwise. Of a half circle radius r equals to 0.2 meter, and 3 straight section. So this part is out of the magnetic field. This semicircle is inside the magnetic field. The half circle lies in the uniform magnetic field. So this B field is uniform. That is directly out of the page. The field magnitude B is like this, as T is larger than 0. So this is always larger than 0, which with B in Tesla and T in seconds. So an ideal battery with EMF, E battery is 2 volt, is connected to the loop. The resistance of the loop is 2 ohm. So there will be a 1 ampere current. So what is the if there is there will be one ampere current if there is no magnetic field, but here we have magnetic field, so the current is not always 1 ampere. What are the magnetic magnitude and direction of the EMF induced around the loop by the field at t equals 10 seconds? Okay, so let's consider the induced EMF, which is d phi b dt. Actually, we don't necessarily need to use the absolute value and determine the direction all by calculation, but actually we can just consider the magnitude and then we consider the direction by Lenz law. So this is d dt b times a, and for this case a should be a constant, and then we have db dt as the b is the function of time. B is a function of time. So a is nothing but pi r squared over 2. Pi r squared over 2 because this is a semicircle. And then d dt. So for the first term, it is 8t. For the second term, which is 2 plus 2. For the third term, constant, take the derivative, should be 0. Right. So now we consider the EMF at t equals 10 seconds. 10, not nanosecond. 10 seconds. So we plug in all the values. R is 0.2 square over 2. And then 8 times 10 plus 2. So this one should be 5.2 volt. 5.2 volt. So and then we need to consider the direction. Well, actually, the rate of change is also positive. It's also positive because you can see here the rate of change here as t is 10 seconds. This one is positive. This one is positive, which means that this magnetic field is increasing. With respect to the time. So which means that for this loop, it should generate a B field pointing into the page. So the induced current should be in this direction. So this is EIND in this direction. So it should be clockwise. So EIND is clockwise. Any questions? Okay. So next, what is the current in the loop at t equals 10 seconds? So as we know that we have EIND to be 5.2 volts, and this one is 2 volt. This one is 2 volt. The loop is 2 ohm. So I should be E net over R, which is EIND minus EBAT over R. So it is 5.2 minus 2 all over 2, which is 1.68. 1.68 should be in this direction. This is I. Because this one is larger than this one. Any questions? 有没有问题？应该 let's consider another sample problem. So the figure shows a rectangular loop of wire immersed in non-uniform and varying magnetic field that is perpendicular and direct into the page. The field's magnetic magnitude is given by this one, so it is always positive. Yeah. Yeah, so it's related to the x-axis, and also related to the time, So the loop have a width 3 meter and a height 2 meter. What are the magnitude and direction of the induced EMF E around the loop at t equals 0.1 second? 0.1 second. So now it is not a constant B field, constant over the loop anymore. So actually we need to use the integration rather than just a simple multiplication. So phi B should be this one using the definition of the magnetic flux. And as long as we know that the B field is perpendicular to this loop, so we can simply write it as BdA. BdA. Just remove the vector. And actually, A is we can further make some simplification because this is not related to the right y-axis, which means that dA should be h times dx. So we have bh dx, and then we can integrate from 0 to w. No, 0 to w. Yes, 0 to w. 0 to w. So now we can substitute all the numbers. Yeah, actually, this is 0 to w. And b should be 4t squared x squared. And then h dx. So we can just move out the term which is not related to x. So we have 4t squared h, 4t squared h. And then we have integrate from 0 to w. We have x squared dx. So let's plug in the values. Sorry. So we have 4 t actually we keep the t square here. And h is 2 meter. So 2. And then width is 3. Width is 3 meter. And then x squared dx. So we have 8 t squared, and then this one should be x cubed over x cubed over 3, and then we evaluate it at 3 and 0 and subtract them. So finally, it should be 72 t squared. We don't actually substitute t equals 0.1 second here yet, because we need to take the derivative with respect to time. If we just substitute t equals 0.1 and then take the derivative with respect to time, then it will be constant and then it will be 0. So E should be d phi b dt, So d 72 t squared over dt, so which should be 144 t, and then we substitute t equals 0.1, so it should be 14.4 volt. So what are the magnitude and also the direction? As long as the B is increasing, and so as phi B is also increasing. You can check here. Phi B is 72 t squared, which means that if t is increasing, of course t is start from 0. So and at very least at t equals to 0.1, this one is increasing. Which means that the induced EMF should be out of the page. And in this case, using the right hand rule, we know that the EMF should be counterclockwise. So it should be counterclockwise.